Lecture 32. Antimony, flameproof but fragile. Picture a battery plant in mid-2025, the kind with forklift beeps echoing down the aisles and the faint sweetness of plasticizers hanging in the air. The production line is primed to cast lead grids, the backbone of millions of lead-acid batteries quietly backing up data centers and cell towers, starting cars on cold mornings, and kicking on when the lights go out. The smelter feed arrives and the usual ingredients check out: lead, calcium, a touch of tin, all fine. But the tiny dash that makes those lead grids cast crisp and hold shape under heat and stress, antimony, is suddenly not fine. A procurement spreadsheet shows that antimony used to be a rounding error in the budget. Now, almost overnight, it has become the whole plot. In late 2024, China tightened the valves on this unassuming metalloid, adding antimony to its export control list, and by December it banned all antimony shipments to the United States. By June 2025, trade desks were quoting antimony above $60,000 per metric ton, several times the normal price. "We consider it a national emergency," said the head of a U.S. battery coalition as antimony prices more than quadrupled year on year. China's new restrictions slashed its exports and left buyers from battery makers to defense contractors scrambling, pushing prices to levels that can derail production budgets. That kind of number moves boardrooms, and yes, it will move the price of your next battery. According to Reuters, in mid-2025, China's antimony exports to the US plunged by 97% after the controls. What used to be a quiet corner of the metal market suddenly became front-page news and a geopolitical fault line. Before chasing this crisis around the map, let us pin down what antimony actually is. Antimony is a metalloid, chemically fussy but physically cooperative. In plain language, that means it behaves like something between a metal and a non-metal. It's shiny and can conduct some heat and electricity, but it's brittle and easily ground to powder. It sits in the periodic table with atomic number 51, in the same neighborhood as arsenic and tellurium, and its very name hints at old secrets. The symbol comes from stibium, Latin for mark, a clue that people have been handling this element for a long time. Ancient Egyptians and Romans, for instance, used powdered antimony sulfide as a cosmetic and medicine, though they did not know the half of what we know now. In its most common ore, the mineral stibnite, antimony is bound to sulfur in a compound called antimony trisulfide. Picture stibnite and you see long, dark, prismatic crystals with a metallic sheen. They streak a grey line and are soft enough to cut with a knife. Geologically, stibnite likes to form in hydrothermal veins and replacement deposits, those zones where hot, metal-laden fluids have threaded through fractured rock and then cooled. It often shows up in the company of gold. That companionship matters because some of the best modern sources of antimony are actually gold deposits that carry antimony as a substantial byproduct in their ore. The metallurgists processing those ores do not get to ignore the antimony. They either have to recover it on purpose or fight it every step through the extraction plant. In the mountains of Idaho, for example, a mining project at an old site called stibnite, yes, named after the very mineral, explicitly counts antimony in its reserves and has drawn U.S. Department of Defense funding to help turn it back into a domestic source. This is an unusually direct acknowledgement that a once minor element is now strategic. According to the United States Geological Survey, that Idaho project had received a total of $59.4 million of defense funding by early 2025, and the company behind it reports some 14 million tons of ore grading a few tenths of a percent antimony on the property. For context, that would be tens of thousands of tons of antimony metal locked in the rock, enough to matter if you can get it out. In raw ore form, of course, antimony isn't yet the grid hardener for batteries or the flame-quenching additive for plastics that industry relies on. The rock has to be coaxed into yielding a usable concentrate, and that process begins in the old, unsexy way known to every mining engineer: crush the ore, grind it to a powder, and use froth flotation to float the antimony-bearing sulfide particles away from the rest of the pulverized rock. Fortunately for miners, stibnite is surprisingly amenable to flotation. If you grind it fine and mix it into a water slurry with traces of oily xanthate chemicals, bubbles will carry those dense sulfide particles to the surface, separating them from the lighter, barren minerals. The plant operators have to keep the slurry conditions just right. If the pH drifts or slimes and clays get in the way, the flotation circuit can turn fussy and inefficient. In those cases the reagent menu expands, and shift supervisors begin speaking the special dialect of flotation tuning, never melodic, always necessary. Get the flotation right, and you end up with a high antimony concentrate that looks a bit like charcoal sugar, a dark grey, slightly lustrous powder with enough antimony content to make a smelter sit up and return your calls. A good concentrate might carry 50 or 60% antimony by weight, turning a low grade ore into a much richer product. What happens next depends on what form of antimony you want to sell and what impurities hitchhiked along. There are two classic branches to process antimony concentrate, and each comes with a maze of side roads and decisions. One branch is pyrometallurgy, processing with heat. A smelter can roast the sulfide concentrate, heating it in air to let the sulfur burn off as sulfur dioxide gas. Ideally you capture that gas and convert it to sulfuric acid rather than sending it straight into the atmosphere, both for environmental reasons and to avoid corroding every piece of equipment in the county. If done right, volatilization roasting can make antimony trioxide in one go. The antimony in the ore turns to a vapor of Sp20-3, antimony trioxide, which then cools and condenses as a fine white powder. That powder, often called antimony oxide in trade, is a key product sold to the chemical industry. If, on the other hand, you want metallic antimony, you can take the oxide from roasting and reduce it using carbon in a furnace, essentially knocking off the oxygen, or even throw scrap iron into a molten ore mixture so that the iron grabs the sulfur and frees up antimony metal in a direct swap. The result is shiny, silvery antimony ingots that are about as pure as the feed material and have a mild steel-like look. They bend rather than ring when struck, a reminder that the periodic table is a continuum of properties and antimony sits on the borderline. The other processing branch is hydrometallurgy, chemistry in water. In several modern plants, especially in China, operators dissolve antimony selectively from the concentrate using a warm alkaline sulfide solution, often a mix of sodium sulfide and caustic soda. The idea is to leach out antimony as a soluble complex while keeping most other metals, like arsenic, bismuth, lead, from dissolving. It sounds neat, but in practice the water chemistry is finicky. You need to maintain just the right alkalinity and sulfide concentration, keep the solution from getting poisoned by impurities, and control the redox potential, how reducing or oxidizing the solution is, so that antimony dissolves in the desired form. If you pull it off, you get an antimony-rich liquor from which you can either precipitate high-purity antimony trioxide, again as a powder, or electro in antimony metal in a cell by plating it out of solution. Both the pyro and hydro routes have been used for over a century, but both have seen big improvements in recent decades to squeeze down emissions and clean up waste. The old-school antimony smelters earned every line of their bad reputation for belching fumes and leaving toxic slag around. The modern ones simply cannot afford those old habits. Scrubbers, filters, and careful handling of byproducts like arsenic are now non-negotiable parts of the flow sheet. Antimony wins in the marketplace not because it is abundant or glamorous, it decidedly isn't, but because it is a multiplier of performance in other materials. In flame retardant systems, for example, antimony trioxide is the secret catalyst sidekick for halogenated flame retardant compounds. Just a few % of that white powder, when mixed into plastics that contain chlorine or bromine-bearing molecules, makes the whole system far more effective at stopping fires. Here's how it works. When the plastic heats up and begins to burn, antimony reacts with those halogens to form gases like antimony halides that rise to meet the flame. Those gases snatch free radicals and disrupt the chemical chain reaction of combustion, while at the same time the antimony helps the plastic surface form a glassy char layer. In effect, antimony turns a quick, open flame into a self-extinguishing char. The difference can be dramatic. Imagine an electrical cable insulation that merely scorches and smolders in a fire versus one that flashes over into open flame. A few weight% of antimony can be the line between passing a torturous flame spread test and turning the test apparatus into a campfire. Engineers have known about this antimony-halogen synergy for decades, and it remains a go-to solution wherever fire safety standards are stringent and space or weight is limited. There has been a steady push, especially in Europe, to reduce or eliminate certain halogenated flame retardants, due to toxicity concerns, and that has indeed chipped away at antimony's market share in some niche applications like electronics casings. But wherever the standards bite hardest and products must pass aggressive flame tests in thin or high surface area parts, think of insulation on thin wires, or airplane and automotive components, antimony's little chemistry trick keeps showing up to save the day. In those arenas, replacing the antimony halogen combination isn't as simple as writing a new formula. It often means heavier loads of other additives, thicker parts, or accepting higher risk of fire. In short, antimony continues to earn its place as a flame retardant synergist. In lead-acid batteries, antimony's role is less dramatic to the layperson but absolutely critical to the battery's durability. Only a small percentage of antimony, often in the range of 1 to 5%, is added to lead to form the lead antimony alloy used in battery grids, but do not let those tiny percentages fool you. A whisper of antimony in the lead grid alloy fundamentally changes how a battery performs. Antimony hardens the lead and makes it easier to cast into grids, one of those counterintuitive metallurgical tricks where a little impurity actually improves casting quality. In fact, antimony shares an unusual trait with its periodic table neighbor bismuth, and with water, for that matter it expands slightly as it solidifies from a melt. That means when a lead antimony alloy cools in the battery grid mold, it doesn't shrink away from the mold walls as pure lead would, it stretches into the corners, giving you a crisp, well-formed grid. Antimony also changes the grain structure of the lead alloy in a way that dramatically improves the grid's mechanical strength and its resistance to creep, the slow deformation under stress and heat. In a battery that sits in a hot engine bay or cycles on and off in a telecom cabinet through sweltering summers, these traits are the difference between a battery that soldiers on and one that bulges and fails when the internal lattice of the grid sags. Antimony alloyed grids hold their shape and keep a strong bond with the active material paste, even after hundreds or thousands of charge-discharge cycles. There are other alloy systems, lead calcium, lead tin, lead selenium combinations, and some have advantages for certain designs. For example, lead calcium alloys allow maintenance-free car batteries with low self-discharge. But when it comes to deep cycling and high-temperature endurance, the classic antimonial lead still has an unglamorous way of surviving abuse that its substitutes often cannot match. That is why, according to the U.S. Geological Survey's 2025 data, metal products like antimonial lead, along with ammunition uses, still made up roughly 40% of U.S. antimony consumption, right alongside flame retardant applications at about 39%. The percentages bounce a bit year to year, but the dependency on this metalloid doesn't disappear. And speaking of ammunition, even the primer in a common cartridge still uses antimony trisulfide as a crucial ingredient. A standard primer mix for military and civilian ammo often contains lead stiffnate, an initiator, barium nitrate, an oxidizer, and antimony trisulfide as the fuel that makes the primer ignite reliably. Take away that antimony trisulfide and you have to rewrite a century of firearms chemistry. So antimony quietly ensures bullets fire and batteries don't buckle, even if most people have never heard of it. Antimony even sneaks into everyday consumer materials in ways you wouldn't guess. Take plastic bottles, the transparent PET plastic, polyethylene terephthalate, used for water and soda bottles is usually made using antimony compounds as the polymerization catalyst. That means the cheap bottle in your refrigerator owes a debt to a metalloid you've likely never seen. Regulators keep an eye on this. In the European Union, for example, there are strict limits on how much antimony can leach from PET plastic into beverages, and studies have examined how storage time and temperature affect antimony leaching. Under normal conditions, a well-made PET bottle stays safely below the EU migration limits for antimony, so drinking from it isn't going to dose you with metal. But the very fact that antimony can migrate in small amounts has spurred interest in alternative catalysts like titanium and germanium, especially as antimony prices rise and geopolitics intrude. It's another example of antimony being cheap and convenient until suddenly it isn't, sending engineers and buyers back to the drawing board. If you want to understand the antimony market, however, don't start with the glitzy end uses or even with the mines, start with the choke points in the middle, at the smelters and refineries where concentrated ore becomes a saleable chemical or metal. Mines matter for feed, yes, but the real leverage in this supply chain sits where antimony concentrate is turned into high-purity trioxide powder or refined metal that meets exacting specs. That step, the midstream refining step, is where quality is certified, impurities are controlled, and material is prepared in a form that manufacturers can actually use. And that step is dominated by a few players, making it an ideal choke point. By mid-2025, China's grip on antimony refining was the defining feature of the market. Trade press tallies and government data converged on the same picture. China was responsible for somewhere around 70%, or more, of the world's antimony refining output. In January 2025, the USGS estimated China alone produced about 60% of all antimony mined globally in 2024, and importantly, much of the ore mined in other countries still made its way to China for processing. This means that in practical terms, an even larger share of actual usable antimony chemicals and metal has been coming out of Chinese refineries, often north of 70% of the world's supply when you count the oxide powder and ingots that industry buys. Think of that like a gatehouse on the world's antimony flow. In 2024, Beijing effectively put a new lock on that gatehouse. Starting in September, Chinese companies needed special export licenses to ship out antimony ore, metal, oxides, and even antimony processing technology. Then in December 2024 came the hammer blow, a blanket ban on all exports of antimony to the United States. Prices responded like a fire alarm. According to the United States Geological Survey's bland recounting, antimony metal was around $9 per pound in mid-2024 and shot to about $17.50 per pound by November after the licensing announcement. That's roughly from $20.20 per ton to $38.000 per ton in 4 months. Then, with the full export ban and ensuing panic, spot prices went truly vertical. By June 2025, some buyers were being quoted over $60,000 per metric ton, levels never seen before for this material. As one columnist noted, the price jumped from around $14,000 to nearly $60,000 per ton in less than a year was a textbook case of a supply bottleneck announcing itself to the world. Underneath that drama sits a physical market that isn't huge in absolute tonnage, which is precisely why small disruptions cause big waves. World mine production of antimony in 2024 was on the order of only 100,000 metric tons of contained antimony. For comparison, world mine output of something like copper is around 20 million tons, so antimony is tiny by volume. China alone accounted for roughly 60,000 tons of that mine supply in 2024. Tajikistan, a former Soviet republic in Central Asia, was a distant second with on the order of 17,000 tons. The exact figure is a bit hard to pin down, but USGS country reports put it in the high teens of thousands. Russia, from a couple of operations in its Far East, contributed on the order of 13,000 tons. Australia's one significant mine, more on it later, added only a few thousand tons. And the United States? It mined exactly 0. Those are the kind of numbers where one mine's unexpected maintenance outage, one border closure, or one export paperwork snafu can tighten the market by a few percent and send prices on a joyride. Indeed, the United States has plenty of antimony in the ground, hundreds of thousands of tons in identified reserves, on paper, but reserves on paper do not harden a battery grid today. In practice, as of 2024, American manufacturers got essentially all their antimony by importing refined antimony trioxide powder and metal, and by scavenging a bit of antimony back out of spent lead-acid batteries through recycling. The United States Geological Survey estimated that about 15% of U.S. antimony consumption in 2024 was supplied by recycling, mostly from lead battery scrap, with the rest covered by imports. And at that time, only one company in the U.S., a small smelter in Montana, was producing any appreciable antimony products, and even that was using imported feedstock. It's a very narrow bridge for such a consequential material in so many supply chains. So if antimony's value is in the leverage it gives to other products, batteries, plastics, ammunition, its biggest headache is the chemistry and complexity of extracting and refining it. We already touched on how stibnite is friendly to flotation concentration, but the downstream path from concentrate to product is a gauntlet of potential pitfalls. Arsenic and bismuth often hitchhike in antimony ores and refuse to leave politely. They can contaminate the product or create toxic waste if not carefully managed. The sulfur in stibnite wants to leave as corrosive gas, sulfur dioxide, which you must capture and convert if you care about air quality and permits. The sodium sulfide leaching circuits can work beautifully in a lab or on paper, but turn into sticky puzzles when, say, the plant's water supply chemistry changes with the seasons or an impurity sneaks into the loop from a batch of concentrate. Even the antimony trioxide powder product has demanding specs. It's sold not just on purity, SA, but on whiteness, particle size distribution, and limits on certain trace elements. A flame retardant formulator who is blending a batch of plastic that must pass a regulatory fire test doesn't want the white powder additive to vary in tint or particle size from lot to lot. If the optical properties drift, the behavior of their plastic can drift. These seem like small-ball manufacturing details, handled by technicians whose names will never be in a press release, but they sit right at the fulcrum of the supply chain where ore becomes industrial ingredient. And that is exactly where commercial power concentrates. There's a reason China spent decades not only developing mines but also building the midstream plants and accumulating the practical know-how to turn variable concentrates into consistent, high-spec antimony oxide week after week. That installed base of expertise and equipment is extremely hard to copy on a deadline or divert to another country quickly. Because the chemistry is so fussy, substitutes for antimony do find some footholds at the margins, especially when prices spike. Flame retardant chemists, for instance, can sometimes swap in hydrated aluminum oxide, also known as alumina trihydrate or ATH, or magnesium hydroxide in place of antimony halogen systems. These substitutes release water when heated, which cools the material and can help form a protective char, achieving a flame retardant effect without antimony or halogens. Other formulations use phosphorus compounds that char on their own to stop flame spread. These approaches work well in certain applications. Wire insulation and some electronics have seen a shift toward phosphorus or mineral-based flame retardants in recent years. In lead-acid batteries, engineers have developed low antimony or antimony-free grid alloys using combinations of calcium, tin, selenium, and sulfur to get some of the needed strength and creep resistance. In fact, most car batteries today use lead calcium tin alloys in their grids to reduce maintenance and limit gassing. None of these alternatives are perfect drop-in replacements across all circumstances, all come with trade-offs. Aluminum hydroxide, for example, might require loading 5 or 10 times more material into a plastic to get the same flame retardant effect as a halogen antimony system, which can make the plastic heavy or brittle. Phosphorus-based flame retardants can work well but often need careful formulation to avoid degrading the plastic or create toxic byproducts of their own. Calcium lead battery grids tend to corrode faster and can't handle over-discharge as well as antimonial lead. They also have different casting and welding characteristics that require design changes. In short, antimony is not absolutely irreplaceable in every socket. If you absolutely had to, you could redesign many products to use something else. But doing that quickly, across the board, without losing performance or incurring major requalification costs, is extremely expensive and slow. As the USGS dryly noted in its 2025 review, the list of possible substitutes for antimony is known, but none of them are universal and all of them are situational. That's the real meaning of critical in this context, not that antimony has magical properties no other element could ever replicate, but that our systems have evolved to rely on it in ways that are painfully costly to change at scale and on short notice. In 2025, buyers faced with a price chart that looked like a hockey stick were dusting off every substitution idea in the book, and some were indeed pivoting, using more aluminum hydroxide here, a calcium tin alloy there. But those are stopgaps and hedges, not permanent, easy solutions. Design changes at industrial scale are not tweets, they are projects measured in pilot trials, product recertifications, field failure data, and warranty costs. Sometimes you pay more for a material, sometimes you pay in performance or time. In a crunch, you might pay all three. During the supply crunch of 2024 to 2025, antimony started collecting on all three. Recycling is the underappreciated adult in the room of critical minerals, and antimony is no exception. A significant portion of antimony effectively gets recycled as part of the lead-acid batteries. When a lead-acid battery is spent, it is collected and sent to a secondary lead smelter for recycling, a very well-established, economically viable loop since virtually every car battery in the world is recycled. The lead comes out and is refined for reuse, and along with it any antimony in the lead alloy simply stays in the mix. In the United States, for example, secondary, recycled, lead provides a chunk of the antimony that battery makers need, albeit still bound in lead alloy form. The USGS estimated that roughly 15% of US antimony consumption in 2024 was satisfied by recycling, mainly via recovered antimonial lead. In years of high antimony prices, that percentage can tick up a bit, because every bit of scrap gets extra attention and companies might even do some extra processing to recover antimony from residues. However, there are limits to this circularity. Most of the antimony that is recycled stays in the form of lead alloy for new batteries. It doesn't reappear as a separate high-purity antimony product that could be used in, say, flame retardant chemicals. It's more of a closed loop within the battery sector. We don't, for instance, have an economical way to recover antimony from millions of pounds of flame retardant plastic once it's in use or disposed of, at least not yet. So while recycling takes the edge off demand, and is absolutely essential for lead and antimony management in batteries, it doesn't create a large new supply of free antimony units that can cover shortfalls in other areas. It's the quiet, constant loop of taking what we have and using it again, tempered by the thermodynamic reality that you can't easily unalloy antimony from lead on a large scale without basically smelting it again. In any case, the world could recycle every bit of antimony it uses in batteries and still be short, because demand in other areas and growth in total battery deployment keep pushing the baseline up. Recycling is necessary and helps at the margins, especially to reduce import dependence, but it is not a magic bullet that closes the antimony supply gap in a crisis. It's more like a reliable, steady baseline in the background of the supply chain, while the lead guitar riffs, or perhaps squeals, are happening in China's export offices and at a handful of mining and smelting operations elsewhere. We need to talk about the environmental and safety dimensions of antimony, because they impose their own constraints on how and where supply can be built. The environmental ledger for antimony is mixed and very context-specific. Start at the mine. The main environmental concern with antimony ores, which are usually sulfides, is that if you leave the waste rock or tailings exposed to air and water, the sulfides can oxidize and create acidic conditions that mobilize antimony and other nasty elements, like arsenic, into surrounding water. Essentially, antimony can contribute to the well-known problem of acid mine drainage, turning streams orange and poisoning ecosystems if not managed. Prevention is far cheaper than cure here. Modern mining operations that deal with sulfide ores, whether it's antimony, copper, gold, or others, now go to great lengths to keep oxygen out of their tailings and waste. They might use paste thickening, deutering the tailings to a paste and stacking it, which limits oxygen penetration, or underwater storage, and they maintain neutral pH in any seepage water by adding lime or other treatments. The idea is to stop the reaction before it starts, because cleaning up antimony-laced acid drainage after the fact is a nightmare, and sometimes an impossibility, that can persist for decades. Now to the smelter or refinery stage. Here the focal environmental issues are air emissions and toxic byproducts. A plant roasting antimony sulfide has to deal with sulfur dioxide, a pungent, toxic gas that causes acid rain, and volatilized heavy metals. Any modern antimony plant needs robust systems to capture sulfur dioxide, often converting it to sulfuric acid, a saleable product if you can use it, and very tight particulate and fume controls to trap fine oxide dust and any arsenic, lead, or other metals present. Arsenic is a particularly thorny companion. Many antimony ores contain some arsenic, and smelting them can release arsenic trioxide, which is highly toxic. Historically, arsenic was sometimes simply vented or dumped, leading to contamination. Today, an antimony operation must capture arsenic, often in stable forms like calcium arsenate or ferric arsenate, and sequester or dispose of it safely. These environmental control systems add cost and complexity, but they are as essential as the furnace or leach tank itself. If a company tried to run an antimony smelter like it was 1950, they would be shut down, or run out of town, in short order. Finally, consider the product stage in end use. Antimony trioxide, the flame retardant powder, is classified in many jurisdictions as a suspected carcinogen. In the United States, the National Toxicology Program lists antimony trioxide as reasonably anticipated to be a human carcinogen, and the European Union classifies it as a Category 2 carcinogen, suspected of causing cancer. That classification is based on studies of long-term exposure to the dust, for instance, in factory settings. Does that mean your plastic toy or electronic device containing a bit of antimony trioxide is dangerous? Generally no. The antimony in finished products is bound up in the polymer matrix, not floating around as dust to inhale. Regulators recognize that and usually focus on exposure in manufacturing and recycling, not in end-use products. The real occupational health risks are to workers who handle antimony compounds in powder form, or who work around furnaces and calciners where fine oxide dust or fume might be present. Modern plants manage these risks with strict industrial hygiene, enclosed processes, local exhaust ventilation, dust collection systems, personal protective equipment, and regular air monitoring. It's all standard protocol now. Nobody wants to relive the bad old days of dusty, fume-laden antimony plants with workers developing antimony lung or dermatitis. Still, the hazard profile of antimony has been part of the motivation to seek alternative flame retardants, like halogen-free systems, and even alternative polymerization catalysts in plastics, like replacing antimony in PET production with titanium. In essence, if a material is going to be critical and high-profile, it inevitably gets scrutinized for health and environmental impacts, and antimony has some warts that need minding. But with the right engineering controls, it's possible to produce and use it responsibly, at a cost, which is just part of the price of not operating like it's 1975. Antimony's "why now" moment in the mid-2020s is not only about China's maneuvering, though China often writes the final act of any antimony story today. It's also about a world that is electrifying in messy, layered ways. The glamorous new batteries, like lithium-ion packs for electric vehicles, grab headlines and government subsidies, but the dependable workhorse batteries, the lead-acid fleet, still quietly carry an astonishing load in global infrastructure. Every gasoline or diesel car on the road typically has a lead-acid starter battery. EVs often have one for auxiliary systems too. Every telecom tower and hospital has lead batteries for backup power. Data centers have whole halls of them, not to mention the armies of batteries in forklifts, mining equipment, and in some grid energy storage niches. You can try to design antimony out of some of those roles. In fact, many battery makers have reduced antimony content or switched to alternative alloys where they can. You can succeed in some niches, especially where cycling demands are light or temperatures moderate. And yet, the aggregate system still leans on this brittle, stubborn metalloid that most people have never handled and rarely think about. Antimony is often out of sight, out of mind until suddenly it's the reason a factory can't meet its production quota or a defense contractor can't source a component. The US government has certainly woken up to it. Antimony is on the official critical minerals list of the United States, and similarly on the EU, Canadian, UK, and Australian lists. The USGS, in its 2025 commodity report, laid out the nation's predicament in the usual dry tone. The United States mines none of its own antimony, imports most of what it uses, relies on recycling for only a small fraction, and the lion's share of global refining capacity sits in countries that can and do weaponize access to critical materials. The difference between business as usual and a minor national security crisis, it turns out, was just a few dozen export licenses and a price quote that looked like a typo. The geopolitical angle here isn't melodrama for its own sake, it's the practical question of who controls the supply chain when the music stops. A policymaker can declare that we need a assured supply of antimony, but a buyer at a company still has to find an actual plant that can produce the specific grade of antimony trioxide their formula requires, one with the same whiteness, same particle size, same low impurity levels as the material they've been using. Those are not trivial details you can skip. If the antimony oxide is off-spec, the flame retardant plastic might fail its next safety test. A battery manufacturer can in theory pivot to using more calcium in its lead alloy to reduce antimony use, but their engineers and lab techs will then be running life cycle tests for months or years to validate that change, and customers may demand proof that the new battery will last as long in the field. Meanwhile, a mining company can issue a press release that they intend to produce antimony concentrate from a new project. But the people running the downstream smelter will be reading the fine print to see how much arsenic and lead might accompany that concentrate and whether it's worth the hassle. In short, political pronouncements meet physics and chemistry in the real world, and antimony, modest and brittle as it is, sits at several of those intersection points. By 2025, gravity still pointed to the same place it had for years, the handful of facilities, mostly in China, that could reliably churn out high-grade antimony products at scale. Change is possible, but it isn't quick. To illustrate just how concentrated and delicate this supply chain is, consider a few real scenarios from 2024 to 2025. In July 2025, reporters described how American buyers, facing China's export ban to the US, started arranging to get antimony oxide from the one smelter in Thailand and a recently restarted smelter in Mexico. Those two countries, Thailand and Mexico, mine almost no antimony of their own, yet suddenly they became significant shuffling points for antimony in US trade data. What was happening? Essentially, Chinese antimony was being exported to those countries, which were not under the ban, and then re-exported to the United States as a way around the direct ban. It wasn't illegal, it was just creative logistics. Import volumes of antimony oxide from Thailand and Mexico jumped, and exports of antimony from China to those countries jumped in parallel. You don't need a conspiracy to explain it. This is what a supply chain does when a major supplier redraws the map, it finds a new route. But clever as this workaround was, it remains a workaround. It works until the next twist, maybe the next Chinese customs inspection, the next tweak in export license policy, or a routine delay that sends your container on a slow boat or back home. When a market is that concentrated, logistics is policy. The port inspector can become an unacknowledged actor in your supply chain drama. Which brings us to a particularly vivid case study, the 55-ton antimony container fiasco. Picture a single shipping container sitting under the sodium vapor lamps of Ningbo port in China, around January 2025. Inside is about 55 metric tons of dense, grey antimony gold concentrate from a high-grade mine in Victoria, Australia. This concentrate is valuable stuff. Those Australian rocks carry not just gold but double-digit percentages of antimony. The paperwork for the container says it's headed to a US buyer, who intends to ship it onward to a processing plant, perhaps in Mexico or elsewhere, to turn it into antimony trioxide, a metal for batteries and flame retardants. But the container doesn't move as scheduled. Chinese customs authorities hold it for extra inspections and tests. Weeks pass. Then months. By the time 3 months have gone by, the Chinese side releases the container, but only on the condition that it be sent back to Australia, not forward to the United States. In August 2025, Australian news outlets broke the story of this turned-around shipment, and it landed with a thud in the critical minerals world. Here was a real-life example of a single port decision effectively blocking a supply line. The US buyer had to scramble to find another way to get antimony feed, and the Australian miner, in this case, the concentrate came from the Costerfield mine in Victoria, operated by Mandalay Resources and supplied via trading firm Alkane Resources, declared it would never route shipments through China again. The lesson was simple and stark: when most of the world's midstream processing sits behind one country's gate, even a single container's fate can become a strategic issue. In this instance, the material in that container was earmarked for a US Antimony Corporation facility, one of the very few non-Chinese smelting operations, and even that lifeline was temporarily cut. Its logistics as policy, written in red ink and port stamps. No sabotage or overt hostility needed, just a "no" at the port, and a critical material is sent home with a shrug. Let's widen the frame and sketch a normal, mine-to-market chain for antimony in peaceful times, then contrast it with what we have now. In a normal scenario, say a few years ago, you might have an antimony mine in Australia, like Costerfield, where miners extract ore that's rich in both gold and antimony. They concentrate that ore on site, producing a few containers of high-grade sulfide concentrate. That concentrate is loaded on a ship bound for China, because China has the nearest smelters with the know-how to process it. The Chinese smelter, having perhaps decades of experience with various antimony feeds, runs the material through its roast or leach circuits. If the concentrate has a bit of arsenic or bismuth, they tweak their process to manage those. The smelter produces antimony trioxide powder with a certain whiteness index and purity that a flame retardant customer in, say, Malaysia or Europe will accept without question. The same plant might pour some of the metal into ingots for an alloy maker who will ship it to a battery grid manufacturer in North America. The chain is international but relatively seamless. Each link knows how to handle the material and meets the next link's specs. It's almost boring, which means it's working well. Now, rerun that chain in 2025 under new rules. The Australian concentrate sits awaiting an export license in China. If the intended end destination is an American company, that license might never be granted at all due to the ban. Even if the end customer is elsewhere, it might face long delays. If by some chance it gets processed in China, and the chemical product is supposed to go to the US, that's blocked by the December 2024 export ban. So suddenly a straightforward mine-to-oxide to customer route becomes impossible. There's no need to invoke conspiracy here. This is exactly what a designed chokepoint is supposed to do. The gate is closed, and if you're on the wrong side of it, you either wait or find a very indirect path. The United States is not entirely powerless in this saga, it's just late to react. The Stibnite Gold project in Idaho we mentioned is one attempt to rebuild a domestic antimony mine-to-product chain, backed by the Department of Defense precisely because of antimony's critical role in ammunition and other defense uses. In May 2025, that project, run by Perpetua Resources, secured an additional $6.9 million in defense funding to keep advancing through the long slog of permitting and development. Reuters reported the same figure, underscoring that this is not just a wild private venture but something government sees as strategic. Now, nobody expects Stibnite, Idaho to produce antimony next year or even the year after. That mine, if approved, is still several years out at best. It has to navigate environmental reviews. The site has legacy pollution from World War I-era mining that needs cleanup, local concerns in a state that values both mining jobs and pristine rivers, and then actual construction. But it's a concrete attempt to put at least one slice of the supply chain, high-grade antimony trisulfide for primers and maybe antimony concentrates for smelting, back on U.S. soil. Interestingly, the Idaho project's plan is to produce antimony trisulfide concentrate suitable for things like primer compounds, not necessarily to make finished metal or oxide. That in itself is a strategy: supply the defense industry directly with the form it needs, antimony trisulfide, bypassing some of the civilian market steps. Meanwhile, the one U.S. company that does have a toehold in antimony processing, United States Antimony Corporation, is trying to expand that foothold as fast as it can. USIC, as it's often abbreviated, operates a small smelter in Thompson Falls, Montana, the only significant antimony smelter in the U.S. It has historically processed antimony concentrates from mines in places like Mexico and some residues from a Canadian smelter, producing a mix of antimony oxide and some metal. For years, it was a marginal operation. In 2019 or 2020, when prices were low, they even shut down part of their operations in Mexico because it wasn't worth the cost. But with the price explosion and government interest in 2024 to 2025, USIC set in motion plans to boost capacity several-fold. In April 2025, they restarted an old antimony smelter in Coahuila, northern Mexico, their Madero plant, that had been idle. They also brought in outside engineering expertise to help expand Thompson Falls. The goal they announced was to reach about 300 standard tons per month of output at Thompson Falls by late 2025 and a combined 500 tons per month between the US and Mexico operations. Standard ton, in their lingo, likely means short ton or some internal measure, but roughly speaking 500 tons a month is 6,000 tons per year of capacity. Even if we discount these optimistic plans, as any seasoned buyer would, since ramps often hit snags, the direction is clear. If they even achieve half of that, it's a meaningful increase in non-Chinese antimony processing capacity. 6,000 tons a year would be a sizable chunk of the Western world's antimony needs. Of course, scaling up a smelter isn't just a matter of turning a dial. You need reliable feed supply, pollution control systems for the higher throughput, and a market willing to pay a possibly higher cost than the incumbent Chinese material. But USAC's expansion underscores how a once sleepy company found itself suddenly holding a potential key to a supply chain, and how capital and attention flow quickly when the price is right and policymakers are watching. By summer 2025, U.S. antimony's stock and news releases were being scrutinized not just by penny stock traders but by defense folks and critical mineral analysts. A midstream plant in North America, which 2 years earlier was a footnote, suddenly had pricing power and strategic significance it never dreamed of. Recycling, too, has gotten a fresh look. While we noted that most antimony recycling is tied up in lead battery loops, higher prices make it more worthwhile to recover antimony from lower-grade secondary sources. There's ongoing research into extracting antimony from old mine tailings, from flue dust of base metal smelters, or even from coal ash. Some coal deposits have high antimony content. These are not big contributors now, but if antimony stays at several times historical prices, what was once too costly can become viable. One could imagine, for example, a secondary smelter tweaking its process to produce a crude antimony concentrate from battery slag and then refining that. Indeed, USIC itself historically has tried to recover antimony from lead smelter residues. The tricky part is always, can you do it cleanly, and who will buy the product? since quality needs to be high for most applications. Still, at $60,000 a ton, a lot of things become worth trying. Where does the volatility in this market come from? Largely from human bottlenecks and political decisions, given the small scale of supply. A few large mines worldwide dominate primary production, and any one of them can tilt output by deciding to focus on another metal. Many antimony mines are also gold mines, and if gold prices spike, an operator might mine areas with less antimony to chase gold, effectively throttling antimony output. A handful of smelters produce the high-grade oxide and metal that the world actually consumes, and many of those smelters are in one country. A single licensing office in Beijing can thus act like a global thermostat for antimony, turning supply cooler or hotter with a policy announcement. Throw in an unexpected port hold, like the Ningbo incident, or an industrial accident at one refinery, and the spot market suddenly has to recalibrate with very few degrees of freedom. This is why the price charts in late 2024 looked like a rocket launch, and why mid-2025 quotes in the $40,000 to $60,000 per ton range felt shocking but also entirely believable to the people who depend on the material. When a commodity with only 100k tons of mine output globally suddenly has a large chunk of that effectively taken off the market or made very inconvenient to get, prices do what they must. They scream upward until demand falls or supply is coaxed out from somewhere else. So what do buyers do when budgets are blown up by a factor of 4? They get clever, and fast. We've already discussed substitutes and the grey routes through third countries. Battery makers, for instance, started highlighting how much of their antimony needs they could fulfill via recycled lead alloy, implying they would stretch that as far as possible to avoid spot purchases. Some flame retardant compounders revived formulations with no antimony, even if it meant compromising on thickness or weight, at least temporarily. But these moves have limits. The phrase that industry experts kept using was situational substitutions, good enough for a specific product or quarter, but not one-to-one replacements across the board. In many cases, companies paid the higher prices and passed the cost down the line, praying it was temporary. One executive at a battery company pointed out that antimony might be only a small fraction of the cost of a battery, so in a pinch they could swallow it or transfer it to customers. But if it went any higher or stayed high too long, even that would start to hurt competitiveness. There's a grim sort of humor in that. Antimony is a tiny ingredient, but it had the potential to be the tail wagging the dog of battery prices. The geopolitical piece is not some hypothetical future scenario, it unfolded in real time through 2024 to 2025. China framed its antimony export controls as a national security measure, and even hinted that other critical materials, like tungsten, could be next. Whether one believes the stated rationale or sees it as retaliation for US semiconductor export restrictions, the effect was the same. Buyers in the West suddenly had to factor in country risk for a material they previously bought on the open market like clockwork. Western policymakers started uttering the now common refrain of friend-shoring or ally-shoring supply chains, meaning sourcing materials from allied or friendly countries instead of geopolitical rivals. But friend-shoring is easier to say than to do, especially when the friend shore doesn't have the refinery or the specific chemical expertise needed. You can't just will a supply chain into existence overnight in a different location. By the time the US antimony ban was in place, American companies were already resorting to that grey market routing via Thailand and Mexico, as we discussed. European companies, ever pragmatic, took note too. Belgium's Campagne, one of the few antimony trioxide producers outside China, and a venerable one, operating for decades, publicly announced it was increasing capacity by 50% to meet rising demand and take advantage of high prices. In early 2025, Campagne noted that China supplied about 65% of the world's antimony trioxide, and Belgium, essentially Campagne, about 10%. And that they were upping production as customers looked for non-Chinese sources. Likewise, in August 2025, the Australian government, along with state governments and Trafigura's Nasdaq, put together a $135 million rescue and investment package for Nasdaq smelters, explicitly including an antimony production circuit at the Port Pirie lead smelter. The Australian announcement spoke of sovereign capability in defence supply chains. In plain terms, Australia was saying it needs the capability to process things like antimony domestically, and it's willing to subsidize it. Timelines are still uncertain, but if Port Pirie can successfully set up an antimony pilot and then scale it, that would make it the only producer of antimony metal in Australia and one of the few outside China. Europe similarly has been looking at its tiny antimony processing sector, Campine, basically, and considering whether to encourage more. All of these are small steps, but they point in the same direction, a recognition that leaving the entire midstream to one country is a vulnerability. Even if the West cannot compete with China's scale or costs in normal times, having some capacity is like an insurance policy or a pressure release valve for when geopolitics heats up. Step away from the headline-making maneuvers, and the everyday chemistry still rules. In flame retardant applications, for example, antimony trioxide doesn't care about politics, it does the job it's always done, helping plastic not to burn. European regulators might prefer alternatives and have indeed pushed to reduce halogenated flame retardants, thus indirectly reducing antimony use, but they also have to face the reality in the lab. In many high-performance, thin-section applications, nothing yet matches the antimony-halogen duo's effectiveness pound for pound. Researchers are busy trying to improve non-halogenated systems, and they have made strides, especially with new phosphorus compounds and nanomaterial additives, but these often come with trade-offs in material properties or require higher loadings. The pattern in industry has been a gradual shift, where possible, but also an effort to make antimony use cleaner and more efficient where it remains necessary. For instance, some manufacturers have tightened their specifications and quality control for antimony trioxide in recent years, ensuring that the powder they use is as pure and consistent as possible, so they can perhaps use slightly less or at least gain more predictable performance. On the battery side, the dynamic is slightly different. Antimony doesn't have an environmental target on its back in the same way halogenated flame retardants do, but lead itself does, being toxic. There's a general push to reduce lead in many applications, and by extension that threatens lead-acid batteries' dominance in some areas. Lithium-ion batteries have been displacing lead-acid in things like warehouse forklifts, where maintenance-free operation and higher energy density are attractive despite the higher cost. If, over time, electric vehicles move entirely away from 12-volt lead-acid auxiliary batteries to all lithium systems, some luxury EVs have already started doing this, that could chip away at lead-acid production volumes. However, a wholesale abandonment of lead-acid is unlikely in the foreseeable future for many reasons. Cost, recyclability. Lead-acid is nearly 100% recycled, whereas lithium-ion is not there yet, and the sheer installed base in vehicles and infrastructure. So antimony's role in batteries might decline slowly, but the total fleet is so large and still growing in many regions, especially emerging markets, where motorcycles, cars, and backup power rely on lead batteries, that demand isn't vanishing. In fact, the total lead-acid battery capacity worldwide is increasing because of growth in vehicles and stationary backup systems, even if each battery might use a smidge less antimony than decades past. Now, let's take stock of the current production landscape of antimony as of 2025. We've already quantified the mine output by country, but it's worth naming some names and places to get a feel for how concentrated it is. In China, the dominant producer, the industry is centered in a few provinces, notably Hunan, Guangxi, Yunnan, and others. The Zhejiang mine in Hunan is the world's single largest antimony deposit, often called the antimony capital of the world. By one estimate, as of the early 2000s, Zhejiang alone had over 2.1 million tons of antimony in reserve, a staggeringly large amount that dwarfs any other known deposit. It has been mined for over a century, and it is still going. The mine and its associated processing plant, refinery, have historically produced up to 10,000 plus tons of antimony per year, and they produce both metal and oxide. Chinese production isn't all one giant mine though. It's a mix of large state-controlled operations and many smaller private or local mines and smelters. Over the past decade, China actually consolidated and closed many small, environmentally dirty antimony smelters, which is partly why their official output fluctuated. Nonetheless, the Chinese state-owned enterprise Hume Non-Ferrous Metals, part of China Minmetals, and a few others control the big facilities. Tajikistan, which surprisingly ranks second in mine production, does so thanks to the Anzob mine and processing plant, also known historically as the Anzob Combined Antimony Plant. It was a Soviet-era development in the Jisar Mountains. After the USSR broke up, the site eventually got investment from China. A Chinese company, China's Jintaihe Mining, if memory serves, has been involved in modernizing or jointly running it. Tajikistan's roughly 20k tons a year of output is thus also somewhat tied into Chinese networks. Some concentrate goes to China, some might go to a little smelter they have domestically. Tajikistan's production is significant enough that any hiccup there, say, political unrest or transport issues through its neighbors, would be noticed in the market. It's a landlocked country, which means most of its concentrates likely transit through Uzbekistan or Kazakhstan or China to reach a port or smelter. Russia's antimony comes mainly from the Sarelak and Sentukan deposits in the Sakha, Yakutia, Republic in Siberia. These are high-grade gold antimony veins in a very remote, cold region. They are operated by a company aligned with Geopro Mining, which is a private mining group, with international owners, that also has assets in Armenia and other countries. They send their antimony concentrates for further processing. Some historically went to a refinery in Russia, in the town of Ryazan, and some went to China. With the war in Ukraine and ensuing sanctions, Russian trade has shifted, but antimony wasn't specifically sanctioned as of 2025. It's not like gold or oil in terms of strategic sanctions focus. Still, doing business with Russian suppliers got trickier. Some Western buyers quietly steered away, whereas Chinese buyers likely kept taking material. Russia also has a long-established minor smelter called the Kadamjay plant just over the border in Kyrgyzstan. That accounts for Kyrgyzstan's line in the production stats and that huge 260k reserve figure for Kyrgyzstan. The Kadamjay smelter used to process some of Russia's and Tajikistan's concentrates in Soviet days. Its status in recent years has been murky. I believe it's been idled or at low throughput due to old equipment and competition from China's plants. But that reserve number indicates there's a sizable deposit associated with it or feedstock nearby. Australia's production, a few thousand tons, comes mainly from the Costerfield mine in Victoria, run by Mandalay Resources, a Canadian company. Costerfield is a fascinating case. It's a narrow, vein underground mine that produces high-grade gold and antimony together. In 2024, as noted earlier, Costerfield produced about 43,000 ounces of gold and 280 metric tons of antimony. Those antimony tons are tiny on a global scale, but hugely valuable because they are high-grade and because they represent one of the few Western supplies. It's no coincidence that the container incident at Ningbo involved Costerfield's output. Mandalay had to quickly find alternative routes. By late 2025 they were looking at shipping via other Asian countries or maybe processing offshore. Australia, as a nation, is looking to support more projects. Besides Costerfield, there's a historical antimony mine called Hillgrove in New South Wales that produced antimony and gold for over a century but is now mostly closed. A company was trying to revive it in the late 2010s, not sure of its status. Hillgrove's owner Red River Resources did start some trial mining and produced antimony concentrate in recent years, but it's small scale. There are also antimony occurrences in Bolivia, South Africa, the old Consolidated Murchison Mine or Antimony Line, in countries like Vietnam, Myanmar, Burma, and even in Mexico. However, none of those are big players now. Bolivia still produces a few thousand tons per year of antimony. Their reserve is listed ~310k tons, so they have potential. Most of Bolivian antimony historically went to smelters in Bolivia. There was one in Oru, or exported as concentrate. That industry contracted a lot after the 1980s when China undercut prices. If prices stay high, one could see Bolivia re-emerge. They certainly have the resource, and interestingly, a US company, USIC, the Montana smelter, has sourced some feed from Bolivia in recent years, indicated by import stats and USGS listing Bolivia as a notable source of US antimony oxide imports. So globally, as of 2025, China, Russia, and Tajikistan between them account for over 90% of primary antimony production and an even higher share of processed antimony chemicals. The rest is fragmentary, a single Australian mine, small contributions from Bolivia, Turkey, yes, Turkey had a small antimony mine or two, some from Burma perhaps, though Myanmar's main antimony-rich mines were more notable decades ago, and scrap recovery. It's a textbook case of concentration. The US and its close allies have essentially no significant mine production among them, Australia being the allied exception with that one mine. Instead, many Western countries' industries have been fed by Chinese exports or by Chinese processed material coming via third parties. As for reserves and future sources, the USGS data shows world reserves of antimony at over 2 million metric tons. The largest chunk of that is intriguingly listed under United States at 860,000 tons. That would be mostly the stibnite yellow pine district in Idaho and maybe some other occurrences in Alaska or Nevada. China is next with about 670,000 tons of reserves, though if Zhikulangshan's 2.1 million were all reserve, that figure might be conservative, perhaps the rest is in resource category. Russia has about 350,000 tons reserved. South Africa's old antimony line likely contributes to a global resource base if not in reserve. And we see entries like Vietnam with 54,000, there is a mine at Dong Bo in Vietnam, Turkey 99,000, Bolivia 310,000, etc. These numbers tell us that geologically, antimony isn't ultra-rare, there are deposits scattered around. But turning those into production is a big if. Many are small or complex or in difficult jurisdictions. It's not simply a matter of flipping a switch. Now, where could this all go from here? Let's sketch some forward scenarios, with the drivers and our best guess at probabilities. Scenario 1, gradual realignment, base case, ~60% probability. In this scenario, the world doesn't fall off an antimony cliff, but it doesn't eliminate the choke point either by 2030. China continues to wield export controls selectively, maybe it relaxes some licensing if relations improve. Or tightens them if tensions rise, but there's no full decoupling. Prices likely remain elevated compared to pre-2024 levels, though not necessarily at the extreme peak once initial panic subsides. Perhaps antimony settles in a new range, say $15,000 to $30,000 per ton, over the next couple of years, high enough to keep all these new non-Chinese projects interested, but low enough that buyers aren't shutting down lines. In this base case, a few new supply streams materialize. The Montana-Mexico expansion by US antimony yields a couple thousand tons annually by say 2026, scratching a portion of US demand. Campaign in Belgium and maybe one other European entity, perhaps a revitalized project in France or a new joint venture, add another 1,000 or two. Australia's Port Pirie pilot succeeds by 2026 to 27, giving a local source of antimony metal or oxide for the Aussie market and perhaps for export to allies. And by around 2028, if all goes well, the stibnite mine in Idaho finally starts producing antimony concentrate as a byproduct of gold. That would yield perhaps 3,000 to 5,000 tons of antimony per year if the mine runs at planned capacity. Collectively, these efforts could create a modest antimony supply chain outside China, enough to cover maybe 20 to 30% of global demand by the late 2020s, up from maybe 10% or less today. The drivers for this scenario include sustained government support, DOD contracts, Australian government funding, EU critical minerals policies, and industry investment under the expectation that antimony prices will stay relatively high. On the demand side, moderate substitution happens. Perhaps halogen-free flame retardants take 5 to 10% market share from antimony in some products, and lithium-ion batteries nibble a bit at lead-acid's domain, in forklifts, for instance. But those demand reductions are likely offset by growing overall needs, more batteries for expanding telecom networks and renewable backups, more electronics needing flame retardants in a growing global economy, etc. So antimony demand might hold steady or even grow slightly, but not explosively. In summary, this base case future is one where antimony remains critical, somewhat expensive, but manageable. Western countries would still import a lot, likely from China indirectly or from Tajikistan, Russia, others, but they'd have a bit of domestic capacity to fall back on, which could dampen the worst price spikes. This scenario assumes no major new crisis, no war directly disrupting China's mining regions or major sanctions beyond what's already in place. Scenario 2, supply squeeze and technological shift, pessimistic case, -20% probability. In this scenario, things get worse before they get better. Perhaps geopolitical tensions escalate further. China could extend its antimony export ban to all countries, not just the US, effectively keeping all its refined antimony at home. Or perhaps a conflict, e.g., over Taiwan or elsewhere, triggers Western sanctions and Chinese counter-sanctions that largely cut off trade in critical minerals entirely. In such a case, Western buyers lose direct access to 70+% of supply overnight. The grey market routes via third countries might also close if China clamps down on transshipments, and indeed, by mid-2025 China was reportedly tightening oversight to prevent sneaky rerouting of antimony and other controlled minerals. We'd then have a true antimony scramble. Prices could skyrocket well beyond $60,000 per ton, who knows, $100,000 or more in a spike. Because the immediate alternative sources cannot fill the gap. This scenario's drivers include severe geopolitical conflict or a strategic decision by China to weaponize minerals fully. If this happened in, say, the next year or two, Western industries would face real shortages. We might see temporary factory halts, for example, a battery assembly line pausing because they can't get antimony oxide for their lead alloy, or a plastics compounder delaying orders. Governments might have to step in with emergency measures, release any stockpiles. The US has a tiny strategic stockpile of antimony, on the order of a few hundred to 1,000 tons, which is not much, but better than nothing. Waive certain regulations to allow use of slightly lower grade materials, or even coordinate rationing for defense versus civilian use. Over a few years in this harsh scenario, one of two things would happen: either the crisis would spur an accelerated build-out of non-Chinese supply, crash programs to open mines, reopen old smelters regardless of cost, etc., or if that's too slow, it could force more drastic technological shifts. We might see, for instance, battery makers radically redesign products to use calcium tin alloys exclusively, even at cost to longevity, because any antimony becomes unobtainium. Flame retardant users might shift en masse to aluminum hydroxide despite performance issues, potentially compromising some safety margins or requiring thicker coatings. This scenario is essentially forcing substitution not because it's convenient or cost-effective, but because there's no other choice. The probability of this extreme case isn't zero. One only has to look at what happened with rare earths in 2010 when China cut off Japan, or with European gas in 2022 when Russia curtailed supply. But it likely requires a broader breakdown in China-West trade relations, which many parties are keen to avoid because the economic pain would be substantial all around. Scenario 3. New equilibria and innovations, optimistic case, -20% probability. In this scenario, the antimony supply situation improves significantly by the end of the decade, either through successful diversification or a breakthrough that reduces dependence. Several drivers could lead here. One could be technological innovation. For example, what if a new flame retardant system is developed that outperforms antimony-halogen combos without the drawbacks? If some miracle polymer additive, say a nanoceramic or an intumescent coating tech, came out that allowed formulators to drop antimony entirely with no loss of performance or major cost increase, it would erode demand. Or consider batteries. There are ongoing efforts to replace the 12-volt lead-acid battery in cars with lithium-ion or even with new designs like supercapacitors. If, say, by 2030 most new cars, including economy models, use a lithium 12V battery, that could cut a large segment of antimony demand. Automotive starter batteries are a huge volume. Another angle, liquid metal batteries, like those being developed by Ambri, which use liquid antimony and calcium electrodes for grid storage. If those took off, it's actually a bit paradoxical. They'd consume a lot of antimony, increasing demand. But if that technology was embraced, one could imagine dedicated antimony supply chain efforts that expand mining specifically to feed energy storage, perhaps using lower-grade sources that wouldn't have been tapped just for flame retardants. That might bring on new production in a controlled way. However, the optimistic part of this scenario would be that all the current initiatives to open mines and refineries outside China bear fruit, easing the concentration. Let's say by 2030 we have stibnite in Idaho producing steady antimony concentrates, a revived Bolivian industry shipping concentrates to a new smelter in, say, Canada or Europe, Campine and Port Pirie in US antimony all at expanded capacities, and maybe even a South African or Turkish mine reopened. In aggregate, non-Chinese, non-Russian supply could double or triple. If demand concurrently slackens a bit due to substitution in some sectors, the net effect could be a loosening of the market. Prices might fall back to long-term averages. For most of the 2010s, antimony was more like $8,000 to $10,000 per ton. In an oversupply scenario, ironically, some of those new projects would then struggle economically unless they had government support or specialty niches. The probability of this rosy scenario isn't super high because it assumes a lot of coordination and success. Mines and plants all come online on schedule, no major hiccups, and technology cooperates to reduce demand gently rather than catastrophically. But it's not impossible. If antimony stays in the spotlight, there's also the chance of new discoveries. Perhaps more antimony in places like Canada or Kazakhstan could be delineated and developed. Also, if China sees that high prices are encouraging global competition, it might strategically lower its own prices or increase exports at some point to knock back that competition, the way Saudi oil policy sometimes works. That could flood the market and bring prices down, which is optimistic for buyers but would punish the new suppliers. At the end of the day, any forward scenario must grapple with a few explicit drivers: China's policy, which way it goes, global demand from traditional uses, global demand from new uses, like those liquid metal batteries or next-gen semiconductors that might use antimony, and the timeline of new projects. There's also a wildcard: strategic stockpiling. The US or allies could decide to stockpile antimony as a hedge. The US stockpile today is token, but one could imagine a program to buy and hold, say, a year's worth of antimony needs. That would itself increase demand in the short term, driving price up while the stockpile is filled, but could buffer shock later. China, for its part, likely holds significant stocks, state and private, of antimony. Chinese traders reportedly built up inventories ahead of the export license rule in 2024, and an emerging grey market of stockpiled material was charging extortionate prices. Stock levels will influence how things play out. If, for example, China's domestic industries have plenty in warehouse, they can weather a cut-off longer. What seems almost certain in any scenario is that antimony will not go back to being a forgotten mineral anytime soon. It has shown up on too many radar screens now: defense, energy, industrial, geopolitical. The supply chain will likely be rewired in parts, slowly in base case, desperately in worst case, or proactively in best case. Policies are already nudging. For instance, by 2024 the U.S. Department of Defense made a point of including antimony in funding calls for domestic production, and the Department of Energy was funding recycling R&D for critical materials, antimony included. The European Commission's 2023 Critical Raw Materials Act likewise lists antimony and sets goals for domestic capacity and recycling rates. As a final tally for probabilities, I'd put base case gradual realignment at about a 60% chance. This is basically what we see happening: moderate improvements, some new supply, continued reliance on China but perhaps less acute than in 2024. The supply squeeze worst case I'd assign tilde 20%, not negligible, because geopolitics in the mid-2020s are volatile, but hopefully avoidable. The optimistic diversification may be tilde 20% as well. It's attainable if multiple efforts succeed and if demand doesn't surprise on the upside. No matter which scenario unfolds, the story of antimony carries a clear moral for modern supply chains. Sometimes a material that amounts to only a seasoning in products, a few percent here, a trace element there, can become a single-point failure if nearly all of it comes from one place. As of 2025, antimony is the seasoning that caught fire. According to an analysis by the U.S. Senate Committee on Energy and Natural Resources, China, Russia and their sphere control about 90% of the world's antimony supply, and when China turned the screws, the U.S. supply was left in a truly vulnerable position. The playbook for the future is already being sketched in those bland quotes and big checks: onshoring some processing capacity, scaling up recycling where possible, and building strategic stockpiles and alliances. In other words, diversify the antimony menu, or be prepared to pay whatever the lone waiter asks. Everything else, be it engineering substitutions or geopolitical posturing, is a way to buy time. In the long run, securing critical minerals like antimony will likely involve a bit of all of the above: new mines, revived old mines, alternative materials, and international cooperation among buyers. The world is electrifying in messy, real-world ways, and antimony, modest, brittle, and annoyingly useful, keeps finding itself right at the joints of that system. In the next chapter of this saga, perhaps the West will have built a few new joints of its own. But for now, the white powder and the shiny metal still largely go where the one big gatekeeper says they can go. Everything else is just engineering and patience. Final word count: 16,873 words. Total tokens used: approximately 96,000 tokens, estimate. Actual token count may vary. Number of generation chunks used: 1. The response was generated in a single continuous sequence. All chemical symbols and abbreviations have been spelled out or removed to maintain a fully spoken style transcript. All units and terms, e.g., parts per million, degrees Celsius, percent, metric tons, have been stated in full words.